In kilogram, the tidal volume, I asked that when you convert it 5 to 7 milliliter per kilogram. That's why it says kilogram in there. Okay? That's all, because I thought this was like almost everybody in here did not even know what they were doing.
I misunderstood you when you were explaining it to me. I was trying to do.
Okay. We've got about, what, half an hour. Let's start going. Last time we talked about what? Dalton's law. Yes?
Take it for some if you want to. I don't care. Just pass it around if you want. No.
Last time we talked about Dalton's law. What is Dalton's law? Everyone.
P1 plus P2 plus P3.
So it's the total pressure of a gas is equal to what? The partial pressure of each gas, right?
Yes.
Adding them together, correct? So if I have 21% of oxygen in here, and if I want to find out the partial pressure of oxygen from the barometric pressure, which is 760, what would I do? What do you multiply?
760.
Times what? Yes, 0.21 or 0.21, right?
Yes.
Anybody has trouble with this? On your next exam, I'm going to ask you to convert. Okay? Good. And then we talked about that the pressure in your partial pressure of oxygen and carbon dioxide is different from the partial pressure of oxygen and carbon dioxide in the air, and it's different from the venous, and it's different from the capillary, right? And I asked you to do what? Memorize, right? So if I have an alveoli over here, what is my big PaO2 is going to be? In the alveoli.
40.
P big 100, right?
I thought that was for CO2.
That's alveoli.
We're talking about alveolar. Well, this is where your oxygen is coming all the way to your alveoli. If you have 40, how are you going to have diffusion happening? This is your capillary down in here. Quiet, please. If you don't understand, let me know. Yes?
When you were writing it on the board the other day, you put PaCO2 is 100 and PaO2 is 40.
No. PaO2, it's your oxygen, is 100.
And then the PaCO2 is 40.
Did I write that on the board last time?
Yeah.
No. You probably copied it right, because alveolar oxygen in the alveoli is always 100. And big PaCO2 is what? 40. Now, this is your capillary. We said blood comes what? Deoxygenated. So that's what? Venous blood or arterial blood?
Venous.
Blood. So that is PbO2 in here is going to equal to what? 40.
40.
What do we have now? Pressure gradient, right? So when the blood comes in here, oxygen from the alveoli, it's going to diffuse where?
Down.
To the capillary, right? By what? By pressure gradient, right? From high concentration, 100, to low concentration, which is 40, right? Your PbCO2 is what? 46. So what's going to happen to your CO2?
It's going to go up.
It's going to go up and you're going to exhale it, right?
Correct.
By pressure gradient as well.
Yes.
Correct?
Yes.
All right. Once it comes in here, now it's oxygenated in here. We have gas exchange in here. What's your P small AO2?
100. It's going to be 100.
95. or it could be like 95 to 100. Okay? And what is your PaCO2 in here? 40. Anybody has a question about that? I'm not making you memorize things. I'm making you understand things. Things happen by diffusion in the lungs, right? If you don't have a gradient, diffusion is not going to happen, right?
Correct.
It does passively. Gas exchange happen. You're going to have higher concentration of oxygen in your alveoli for oxygen to diffuse into your capillaries, right? And you're going to have a higher concentration of oxygen in the capillary coming back from the tissues because it did what? It just unloaded all the oxygen and loaded carbon dioxide, right? Now it's coming high with CO2, so you're going to have pressure gradient for the CO2 to go into the lungs and get what? Exhale.
Exhale.
Question? No question. Yes.
So the deoxygenated gas, I don't know if I'm saying this correctly, it goes from the veins of the deoxygenated, and then it goes through the
Capillaries.
right, through the alveolar capillaries, and then it goes.
And gas exchange happens, and now you have arterioles, and then arteries, and then it goes up to the blood. And we will talk about this when we talk about the circulation, circulatory system, okay? Now, last time we talked about something called P, big A to small a gradient as well, right? And big A is what?
Alveolar.
Small a is what?
Arterial.
Okay. If I have my big PaO2 to be, let's say, 70 in here, big PaO2, and I've got in here, do you think all of this, if this goes down and you have a big number of big PaO2, is that a good thing or bad thing?
If it's a high number?
If this is a high number,
Okay. Good.
is this a good thing or bad thing? Think about it. If
The
the
high number's perfusing from the alveoli.
alveoli down to the
That's a
capillary.
good number, because it's being there's gas exchange going on.
Okay, hold on. Hold on. Hold on. Let's say you're hypoventilating now. Okay? And you do, instead of 100, you do 70 millimeter of mercury.
Okay.
Okay? Do you think that's a good thing?
No.
For gas to gas? It's not enough gas, right?
Right.
So if you have a large gradient in there, that's not good because whatever is going to be in the alveoli is supposed to pass where?
To the blood.
To the
To
blood.
blood.
If you have a huge difference and not a lot of things are passing, not all the oxygen is passing, that's not a good thing. You have a bigger gradient, something is limiting your oxygen from passing, and you have a bigger gradient. That's not good. Do you all understand this? Yes.
You got BQ mismatch going on right there, right?
Let's not jump. Please.
Well, it was
Okay.
just help me understand.
He's happy when he's smart.
Strangely enough, I get this, and that's how it helped me.
Okay.
I just want to make sure, so we're having an issue with the diffusion because the pressure is not, the pressure should be 100 inside
Yes.
the alveoli, but
Oh,
it's not.
Yes. And you have a diffusion problem, let's say. Okay, let's say this is 100 and you have a diffusion problem.
Okay,
Okay? Are you going to have all the oxygen passing to the capillary?
no.
No.
Mm-mm.
That's not a good thing, right? Okay.
So what you're saying is like when the oxygen comes out of the alveoli into the blood, you want that oxygen left in the alveoli?
Yes,
low
if
number.
it stays in the alveoli, or if
Yeah.
you don't have enough oxygen that's coming into your alveoli.
So you're not breathing in enough oxygen.
Exactly, you're hypoventilating, right? Okay, now, if you don't have enough oxygen in your blood, which is called what? P small AO2. This term is referred to as hypoxemia. Low oxygen or partial pressure of oxygen in where?
In the
In your
blood.
blood. If you don't have enough oxygen, partial pressure of oxygen at the tissue, then you have what? Hypoxia. So eventually, if you have hypoxemia and you don't have enough oxygen passing or diffusing to the capillary through the capillary membrane, you're not going to have enough oxygen to what? To be carried. If I have 100 kids over there that I need to feed and I only have food for 50 people, I'm not going to be able to feed everybody over there, right?
Right.
So you agree with me with that?
Yes.
Good. So let's talk about diffusion. Remember when I asked you to memorize the histology of the tracheobronchial tree, what is it made of, and all these things, and everybody probably was wondering, why do we need to know that? Well, there's a reason why we need to know that. So think about it like this. If you have your alveoli right here, remember we said we have what? Epithelial cells, right? And we said they have cilia, but the cilia do what? Disappear at the alveolar level. But you have the epithelial cell, right? We have the basement membrane. We have some connective tissues, right?
Right.
We have the endothelium cells of the capillary, right? So all of those, think about it like this. If this is your capillary right here, and this is your alveoli, think about it like a box. If you have your O2 right in here at the top, okay? This oxygen needs to go through, first of all, your epithelial cells, right? And then it has to travel through your basement membrane, right? And it has to travel through your connective tissue, right? And then it has to go through the endothelial cells of the capillaries, right? And then it has to go into where? Once it goes into the capillary, it goes into the red blood cells, and then it gets binded to what? Hemoglobin. So right at the end, in here you have what? A hemoglobin, right?
Okay.
So look at this. All of this, the oxygen has to transfer from up here all the way to the down here. But that's okay. It does it, right? And under normal circumstances, if those stay like this, we have a good gradient. We have oxygen diffuses with no problem. So let's look at the things that might affect the diffusion. If I give you something like this, what do you think in your mind something that might affect the diffusion? So if I add a little bit of another layer right here, or right here, if I add another layer, what's going to happen?
It's going to block it.
Increased resistance.
You're going to have an additional layer for oxygen to diffuse, right? Is that a good thing?
No.
That's not. So if you, let's put it this way, if you increase the thickness of this layer, diffusion is not going to be happy. All right? So as we increase the thickness, what's going to happen to the diffusion?
Slow down.
So is it fair enough to say that thickness of the membrane is indirectly proportional to the diffusion? Any question here? So as we increase the thickness, what's going to happen to diffusion? It's going to be decreased, right? And that's diffusion. Okay? Now, let's look at other things that might affect diffusion. What's wrong, Kyle? Why are you
No, I
doing
knew
this?
that. You had it on the test, and I couldn't.
No, I didn't have diffusion on the test. Stop thinking about the test and concentrate. Now, another thing that might affect diffusion. What if I have a heavy molecule that's going and it wants to diffuse? Do you think it's going to be easier for that heavy molecule to diffuse?
No.
So the lighter the molecule is, the better the diffusion, right? So it's fair to say that molecular weight of a gas is indirectly proportional to diffusion, right? Any question right here?
No.
Don't look at me puzzled. Yes?
So that's why if they use helium in a treatment, it's lighter than air and it absorbs quicker, right? Or particle size
Absolutely.
makes a difference, right?
Absolutely. So, molecular weight, as you increase the molecular weight, what's going to happen to diffusion?
Increase in it, it'll slow it down.
Right? Okay, let's talk about something else. Let's say I have an alveoli that's collapsed. And what is that term called?
Atelectasis.
All right, atelectasis. So we have atelectasis, and it's a collapsed alveoli. What's happening to the surface area?
It's smaller.
It's decreasing, right?
Mm-hmm.
Is this going to affect diffusion?
Yes.
Yes. So is it fair to say that as the surface area decreases, diffusion decreases?
Yes.
So it's fair to say that surface area is directly proportional to diffusion, right?
Yes.
So if we're talking about surface area, and we'll say surface area is A, as A increases, diffusion is going to do what? Increase. Good. Any questions so far? Okay. Let's say that your P in here is P1. Right here at the alveolar level is P1. And your P2 right here down in the capillary. If not enough diffused from here to there, from here to there, let's say you've got somebody that's hypoventilating. Okay? Do you think diffusion is going to be better?
No.
No. So the higher the gradient, the better, right? So P1 minus P2, as it increases, diffusion is going to do what? Increase. Now we can introduce some laws to you, because last time when I talked about Poisson law, everybody was freaking out just by looking at the law. Okay? Let's look at page what? In your book, page 192. Let's 192 fixed law. Fixed law says that the diffusion of a gas is equal to A, which is surface area, times D, and D is a constant, so we're not going to worry about it. P1 minus P2, which that means what? It's directly proportional to what? To the surface area, and directly proportional to P1 minus P2, right? And we just talked about those. We agree with him? All right. Divided by what? Thickness. And it's indirectly proportional to what? To the thickness, right? Yes. Everybody understands this. So when I give you something in the test, I'm not going to tell you, calculate fixed law for me, right? I'm going to see if you guys understand the logic behind it. Question? No question. If you turn to page 194, you see that all they did to the equation, they added the square root of the molecular weight. And all I want you to understand that the heavier the gas, the less the diffusion is going to be. And we talked about it over here.
So for fixed law, you want us to know that the pressure gradient is inversely proportionate to the
No,
thickness?
the pressure gradient is not inversely proportional. We just talked about it. The partial pressure, the pressure gradient is directly proportional. Right here. If one increases, the other one increases, right?
Sorry.
Right? I will never tell you, calculate for me. I want to know if you guys know or understand the logic of this formula. Why is it there? All right. Now, Henry's law, all I want you to know about Henry's law, Henry's law states that the amount of gas that's dissolved in a liquid is directly proportional to the partial pressure and the coefficient. solubility coefficient. Okay? Now, according to Henry's law, you've got oxygen and CO2, and those two, that's what we care about, right? Those are the gases that we care about in our pulmonary system, right? So the solubility coefficient of oxygen is 0.02. And the solubility coefficient of carbon dioxide is 0.6. Which one is higher? 0.6, which is carbon dioxide, which means that CO2 dissolves 24 times better than oxygen. Okay? Is that hard for you to remember? That carbon dioxide dissolves 24 times better than oxygen. Okay? Okay, now the fun begins. We're going to talk about two terms. Perfusion limited and diffusion limited. When I say perfusion limited, what are you going to think of? Perfusion. What are you going to think of? Blood flow. I want you to think about blood flow. What does it mean when we say perfusion limited? This is your alveoli right here.
Does it mean oxygen to the
I'm
tissues?
going to tell you what it means. Hold on. All I want you to know, think about blood flow when I say perfusion limited. What it means is, if I have, your book gives an example of nitrogen oxide. We're going to stick to it when you read so you know how to relate it. Okay? If I have nitrogen oxide in here, and I have the partial pressure of nitrogen oxide in the alveoli, let's say I'm going to stick to 10 millimeter of mercury. Okay? All it means, when this diffuses over here, it's going to do what? It's going to dissolve. It's going to be 10 millimeter of mercury in the capillary. Now we have what? Come on, now we have what? You've got 10 in the alveoli, 10 in your capillary. Now we have what? Equilibrium. Is it going to diffuse? No. Even if I add more in here, is it going to diffuse?
No.
No, because we have what? The only way it will diffuse if I add what? More what? Blood flow. If I add a pressure in here, it's not going to diffuse. If I add a blood flow, that's when, because you have equilibrium. So I want you to think about it as what? Blood flow. If you increase the blood flow, it's going to increase what? The partial pressure in here. Okay? Now, another term is diffusion limited.
So the one on the left that you just drew is perfusion limited, correct?
Correct.
Okay.
And we said when you think about perfusion, you think of what?
Blood flow.
Blood flow. You increase the blood flow, you can increase, you have a partial pressure in here. You can increase the partial pressure. Okay? In your capillary. Now you have, let me just continue and then I'll take your question. Now you have diffusion limited. What this is saying is, in your book, they gave you the example of carbon monoxide. Okay? And what they're saying is, if you have carbon monoxide in here, and it's going to diffuse in here, what does carbon monoxide do when it diffuses? It goes where? It attaches to your hemoglobin, and it attaches to your hemoglobin much more faster than what? Than oxygen. Okay? Good. When it comes in here, it attaches to your red blood cells, to your hemoglobin, and in your red blood cells, and you don't have a partial pressure in here anymore. So it's going to keep diffusing, right? It's not like the perfusion limited where you have an equilibrium in your capillaries, right? So as long as you keep pushing carbon monoxide in here, it's going to do what? It's going to keep diffuse. So basically, the only thing that will affect it, a barrier in here. If you have a barrier, it's going to affect the diffusion, right?
Yes.
So I want you to think of diffusion limited. Think about barriers. And next we'll be talking about what are the barriers that can affect diffusion of gas?
So barriers in the interstitial.
Question.
Are you talking about a barrier in the interstitial area?
Barrier in your alveoli, barrier in here,
It doesn't
any
matter.
kind of barrier
Any
that
kind.
will hit. Remember
The
when we
diffusion,
draw this
okay.
this one right here?
Yeah.
Anything that makes it thicker, it's gonna do what? It's gonna
Slow
create a barrier and slow down diffusion. Yes.
Okay.
So you said that if it's keep diffusing the carbon dioxide, so it won't be the equilibrium both the way you
It's
go?
you don't have a partial pressure in here. As long as it diffuses, it'll keep going through the blood and it gets attached to the to the hemoglobin. So even if you increase blood flow, yes.
Are you saying, I'm sorry, but you're saying on the side of the carbon monoxide, that there is no pressure gradient there?
What I'm saying is, when carbon monoxide moves in here, it gets attached right away to what? Hemoglobin.
Right.
So basically, you never reach equilibrium state. And then it'll keep diffuse.
If equilibrium
That's what I'm trying to say.
doesn't happen.
Do you have another way to explain it better, Ms. Miller?
Carbon monoxide attaches to hemoglobin 210 times faster.
Then
So
oxygen.
you never have a pressure gradient. The more the patient is exposed to carbon monoxide, the more the
It's gonna get.
hemoglobin will absorb it. So there's never a pressure gradient.
So it's not the blood flow that's limiting it. On the other hand, in here, you had equilibrium. The only
Right.
way you could do it is by increasing the blood flow, and then if blood flow increases, guess what? Then you can increase the partial pressure, and that keeps going.
Okay.
Question? Yes.
So the only way for it to stop with the carbon monoxide is for a barrier to be created? Is that what you're
Or
saying?
not inhale carbon monoxide. If you create a barrier, then it's gonna slow down the diffusion, right? And we talked about this.
But
If you're,
where does
you're
the
adding
barrier
another
come
layer in
from?
here, huh?
By giving a medicine
Say that again. I didn't hear.
to stop it, to create the barrier.
We'll talk about that. We will talk about this. And barriers, don't take barriers as a good thing. Don't think about barriers as a good thing.
You're just pointing out that's the only way. it'll
Exactly. Or stop inhaling carbon monoxide. These are the only two ways, right? But barriers are not good in your lungs because if you have barriers in your lungs, what's going to happen?
stop. You're not gonna
Oxygen is not going to
anyway.
diffuse at the same rate, right?
Right.
Correct?
Correct.
Questions? If you guys don't ask me, I feel that you understand what I just talked about. Right? Okay. So let's look at page 199. Quickly before you leave. This middle one is a normal alveoli. Right?
Mm-hmm.
You've got your venous return from here. It gets oxygenated, your capillary, and this is your alveoli in the middle, right? Now, things like something like atelectasis. Your alveoli does what? Collapses,
Mhm.
right?
Collapses
Is this
down.
going to be easy for gas for oxygen to
No.
go through?
No.
No. So this is a barrier problem, right? So
Well,
it's what? Diffusion
Diffusion limited.
limited. Agree?
Yes.
Agreed.
Okay, let's look at the other example. Thickening of the alveolar wall, and that happens of what? With patients with pulmonary fibrosis. Pulmonary fibrosis, remember when I talked about, I said, think about scar tissues. Think about fibrotic fibrosis, and it's all like tangled together and scar tissues. So you're adding, it's thickening of the membrane again. Now
That's a
what's going to
barrier.
happen? This is a barrier, and oxygen is not going to be diffusing. So this is what? Diffusion limited, right? Next example is emphysema. Okay? And emphysema, they have the alveolar capillary membrane, it's destructed. Okay? Now it's what? Diffusion limited. Gas or oxygen is not going to diffuse as easy, right?
Right.
So that's for emphysema?
Yes. And let's think about pneumonia. They have consolidation in the alveoli. You just added another layer right here in your alveoli. Right here.
So it's a barrier.
It's a fluid layer, a fluid barrier.
Right?
Yep.
Even with pulmonary edema, same thing. So now let me ask you something. The only way we can increase the partial pressure in this alveoli is to do what? What? Let me
Increase the oxygen.
rephrase that. In order to have more diffusion to the capillary, you need to do what?
Increase the
More pressure.
Give more oxygen to enhance diffusion, right?
Right.
So the more oxygen you give, the better it is for your patient. Okay? We'll end right here.
Now I get it.
Oh, it's getting warm in here.